common and natural logarithms. Our objective for this video, we want to identify and solve problems involving common, which are base 10, and natural, which are base E, logarithms. To this point, we've got a fair amount of knowledge that we can apply. We know what a logarithmic function is, any function of the form y equals log base b of x, where the base b is greater than 0 and not equal to 1, and the argument x is positive. We know that the log function outputs an exponent. I need to probably change that to the word an. It is the name for a certain exponent. We know that the exponential equation and the logarithmic equation are related. The exponential equation y equals b to the x is equivalent to the log equation x equals log base b of y. And we know all these properties of logs. The log base b of 1 is 0. The log base b of b is 1. The log base b of b to the x is x. The log base b of a product is equal to the sum of the individual logs. The log base b of a quotient is equal to the difference of the log of the numerator and the log of the denominator. The log base b of x to the n is equal to n times the log base b of x. And finally, if m equals n, then the log base b of m equals the log base b of n, and vice versa. The importance for bringing all these back out is that it doesn't matter what the base is, these are all true. Okay, so we're going to look at two bases, two probably the most common bases. The base 10, I'm kind of moving my sheet down here, and base E. Okay, again, so the two most popular are base 10 and base E. Base 10 is called the common log. If you're asked to simply find the log, then that question is asking you for the common log. Find the log of, you're looking for the log base 10. On a calculator in Desmos, it is simply a log button, and I'll show you that in just a moment. And as you know from logs, it is how many times that we need to use 10 in a multiplication to get our desired number. So if you see log with no base written and the argument of 1,000, for example, well, that can be rewritten as log base 10 of 1,000. And of course, 10 to the third power is 1,000. If we rewrite this as an exponential function, we have 10 to the third equals 1,000. And base E stands for Euler's number. He came up with the number E when he was doing compounding of interest, financial application. E is 2.71828, and it goes on forever. It never repeats. It's an irrational number like pi. The base E log is called the natural logarithm. On a calculator, and I'll show you that in just a minute, it's the LN button, which I think stands for log natural. And it's how many times we need to use E in a multiplication to get our desired number. So if you see the natural log of 7.389, for example, that means that this is the log base E of 7.389, and we can put it into the calculator and come up with that, but E, this is approximately E squared, is equal to 7.389. So don't lose track of the fact there's no base written here, but it's assumed it's a base E. There's no base written here, but it's a base 10. Let's just quickly take a look at this in Desmos, and I'll show you it within the functions. So we're going to look in the bottom right here under functions, miscellaneous. Here's the log with the variable base we've been using, and you can continue to use it. You can put E in here, you can put 10 in here. Here's the shortcut. for the common log, just type in the log and it will assume it's base 10. So here's our 1,000 and you get 3. Okay, and go back to the functions. Here's the ln. Again, that assumes base e, so it's a quick way to write log base e. And we were doing ln of 7.389, which as you can see is remarkably close to 2. And it is 2. If you round to the nearest millionth place, you're going to get 2. So that's just stating to you where these are located within the functions of Desmos. Okay, so let's do a couple of problems. I've got 3 here for you to kind of work with these common logs and natural logs. Okay, a first example. Find velocity if the log of v, so there's no base indicated, so we know that means it's the log base 10. Find velocity if log of v is equal to 8.4768, where v is the speed of light. So we have here, this is the log of v is equal to 8.4768. Well, we can write that because we want to solve for the argument, so we're going to rewrite this in its exponential form. So if it'll help us, we can put the 10 down here so we can see it. And then we can write it in its exponential form, base to exponent equals argument. So this becomes 10 to the 8.4768 is equal to v, the velocity in meters per second. And of course, this can go into a calculator, and we have solved for the argument. And I came up with 299,778,167.2. Okay, so the common log, same idea, same thing we've been doing all along. It's just recognizing that when you don't see a base and you see the log term here, that's base 10. Okay, solve for y, example 2, in terms of x. The natural log of y plus 2 times the natural log of x equals 1 plus the natural log of 5. And so we're trying to get everything over onto the other side. Well, let's use we can use some of our properties of logarithms. First things first, I think this 2 can go as an exponent, so I have 2 logs, or 2 natural logs. So the ln of y plus the ln of x squared is equal to 1 plus the ln of 5. Because now I have the sum of 2 natural logs, okay, which is equal to 1 natural log of the product. So this is the natural log of x squared times y is equal to 1 plus the natural log of 5. Okay, if I move my log over, I will have a subtraction which equals the quotient. So I'll subtract, and the natural log of 5, of course, is just a number. I'm just leaving it the way it is here, but it is just a number. So I will subtract the natural log of 5 from both sides, and on the left side, I have the natural log of x squared times y minus the natural log of 5 is equal to 1. And we know the difference of 2 logs is equal to the quotient of the first divided by the second. So this is the natural log of x squared times y over 5 is equal to 1. Okay, so now I have it in 1 log form. I can rewrite it now. I need to get at this argument. I can rewrite this as an exponential form. And we just note that there's an e down here. And so we can do an exponential form. E to the first power is equal to x squared times y over 5. Well, of course, e to the first power is e. So e to the first power is equal to x squared times y over 5. Let us multiply both sides by 5. And I have x squared times y is equal to 5 times e. And now I can solve for y, and I'm running out of space here. Y is equal to 5 times e over x squared. So there's your answer. Okay, this is obviously a positive exponent, but it has a fraction. So we could also write that with a negative exponent and no fraction, 5 times e times x to the negative 2. So pick and choose here. Some folks prefer to have positive exponents and they'll take the fraction. Other folks are saying, I don't like fractions, I'd rather have the negative exponent. Either one of those works. Okay, now more of a real world example here. Get my paper so I can work with it. I think I'm almost there. Just a second. Got to move a few things. There we go. That's what I wanted to be. The distance x traveled by a motorboat in t seconds after the engine is cut off is given by x is equal to k to the negative 1 times the natural log of k times v sub 0 times t plus 1. V sub 0 is the velocity of the boat at the time the engine is cut, and k is a constant. How long does it take to go 150 meters? Well, I bet that is the distance. That's probably x. If v sub 0 is 12 meters per second and our k, our constant, is 6.80 times 10 to the negative third. Well, let's substitute. 150, that's our distance, and that is x. The distance is here, is equal to k to the negative 1. I'm going to need some parentheses here. K is 6.80 times 10 to the negative third, and I want to raise that to the negative 1, times the natural log of k. Okay, I'm going to use brackets to make it look a little cleaner and a little more, make it look a little more structured. K, so k is this 6.80 times 10 to the negative 3 times v sub 0. V sub 0 is 12 times t. Well, we're looking for t, so t is our unknown. And then we have a plus 1 here. And that's kind of messy. That's a lot of stuff. We were just being very careful to substitute in, and we use parentheses or brackets for clarification. I'm going to go ahead and do some math, and I'm going to round my numbers to the, let's say, the 10,000th, just to hold a lot of places. Left side looks good. I don't like all these extra. That's a lot of stuff to carry around. Well, that is, if I do the math on that, 6.8 times 10 to the negative third, all of that raised to the negative 1, is approximately 147.0588. It's a little easier to work with, times the natural log of, well, this times 12, again to the 10,000th place, 4 decimals is 816. So that's, and then you got your t plus your 1. And so that's a little nicer. I just did the multiplication here, and I did this exponent here. And now I need to get at the argument, so I'm going to be using an exponential form to get here. Let's first divide both sides by the 147.0588. So divide the right side by that, and that of course is 1. I'll do the same thing to the left side. And I come up with, let's see, now 150 divided by this. This is 1.02. And this is equal to the natural log of 0.0816 times t plus 1. Okay, I finally have a single natural log. I need to get at the argument, so I'm going to rewrite it in exponential form. I'm going to go the other direction with my circle. Remember, there's an e here. E to the exponent equals the argument. I went in the reverse order, but I still started from the base to the exponent equals the argument. So let's see here. E to the 1.02 is equal to 0.0816 times t plus 1. And now I can finally get at t. Not too bad. I'll subtract 1 from each side. And I'm going to rewrite it with the variable term on the left. 816 times t is equal to e to the 1.02 minus 1. So I subtracted 1 from both sides. Now I'll divide both sides by 0.0816 because I want to get t by itself. 0.0816. And t is equal to this mishmash fraction, e to the 1.02 minus 1 divided by 0.0816. And of course this is an approximation because I did some rounding to the 10,000th places here and there. But that can go into a calculator, and it's going to be approximately 27.73 seconds. How long does it take? T seconds. So there you have it. It takes about t seconds for that boat to go 150 meters per second in this scenario. So very similar, these log problems are still log problems. We still do all the same things. We just recognize that the ln has a base of e. It's just not written, but we can kind of put it in and use it. And that at the very top, the common log has a base of 10. And again, we can write it in there so we can make use of it if we would like to see it.